Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. Up until now, almost everything we've done in math has involved static objects, fixed numbers, fixed shapes, or relationships that don't change over time. Calculus begins when we ask a new kind of question: what happens at an instant? Two classic problems motivated the entire subject of calculus. The first one is finding the slope of a curve at a single point, aka the tangent problem. The second one is finding the velocity of an object at a specific moment in time, aka the velocity problem. At first glance, these seem like completely different ideas. One is geometric, the other is physical. But today we'll see that they are actually the same mathematical problem. By the way, if you haven't subscribed to our channel yet, make sure you do that first so you don't miss out on new weekly content. Now let's start with the geometry problem first. Suppose that we're given a curve, and in this example, the curve is y is equal to x squared. At a specific point, say x is equal to 1, where I have now labeled as our point A, we want to find the slope of the tangent line. Now we'll explain what this tangent line is in just a little bit. The thing is, we've never been asked the slope of a curve before. The only time we've talked about slopes are when we're dealing with linear lines. So a straight line has only one slope. But a curve has different slopes at different points. So what does the slope at a point even mean? So let's try to apply what we already know about slopes to this particular problem. We know how to find the slope between 2 points, and that is going to be m is equal to the difference in y value, so y2 minus y1, over the difference in x value, x2 minus x1. So let's say we're going to pick 2 points. Of course, one of the point is going to be our point of interest, point A, and then we're just going to pick another point B that's a little bit ways away. So for now, we've settled on 2, 4. Now, if we connect those 2 dots, it's going to give us the slope between those 2 points. And this is what we call a secant line. A secant line is a line that touches more than one point. It is not a tangent line, which only touches our curve at our point of interest, point A. But that's okay. We're going to try to find the slope of the secant line first. So we start with our point B with an x value of 2. Now the slope, m, is going to be equal to the y value there, which is 2 squared, since our curve has the equation y is equal to x squared, minus our y1, well, that's our point A, which has a y value of 1, over x2 minus x1, so that'll be 2 minus 1. So this is going to give us a slope of 3. Okay, but I think we can do better than that. So what happens when we try to move our point B closer towards our point A? So let's go ahead and erase this point here. And then what we want to do is now we want to move our point B so that it has an x value of 1.5. So now it'll be right over here. This is our new point B. And now if we draw the secant line between those 2 points, it'll look like this. And let's go ahead and find the slope of this new line. So it's going to be m is equal to 1.5 squared minus 1 squared over 1.5 minus 1. And this is going to give us a slope of 2.5. Cool. So now it seems like we're getting closer. Let's try to do a little better. Now we're going to put our b so that it is right over here, and it has an x value of 1.1. So this is our b. Same thing, we're going to connect those 2 dots. And then this is going to be our new secant line. Now the slope there is going to be equal to 1.1 squared minus 1 squared over 1.1 minus 1. And now our slope is equal to 2.1. But I think we can do even better than that. So why don't we try to go a little bit closer? So we're going to now go to 1.01. So now point B is almost overlapping point A, but they're still different points. So now if I connect those 2 dots, this is going to be the secant line. And now our slope is equal to 1.01 squared minus 1 squared over 1.01 minus 1. And this is going to give us a slope of 2.01. And just for fun, we're going to do one last point. I can't really draw it on there anymore because it's going to end up looking like it overlaps A. But we can calculate the slope there. The slope is going to be m is equal to 1.001 squared minus 1 squared over 1.001 minus 1. And that is going to be equal to 2.001. And of course, you can keep going closer and closer. You can pick the point 1.0000001 and then calculate the slope of the secant line. And what you're going to realize is that number is going to get closer and closer to 2. So now, without knowing the actual way to calculate the slope of the tangent line, by filling out this table, we can make an educated guess and say that the slope of the tangent line at the point A is going to be equal to 2. And we're just going to put a little question mark because we don't know that for sure yet. But the idea of a tangent line is you would imagine that you have a straight ruler, and then what you're going to do is you're going to bring it towards your curve so that the ruler touches your curve at your point of interest. So in our particular case, our point of interest is A, which means that if we bring our ruler closer to A and we only want it to touch our curve at A, it would look something like this. Now let's switch context. Let's take a look at the velocity problem. Suppose that we have an object that moves along a straight line, and its position in meters is given by the equation s of t is equal to 3t squared, where t is in seconds. Now suppose the question is we want to find the velocity of this object at time t is equal to 5. Now the process would be similar as above. Our point of interest is at, let's say, point A, where t is equal to 5. Then we know that the position of the object, s of 5, is going to be equal to 75. Now we can calculate the average velocity of this particular object if we measure its position at another point in time. So let's say at point B, the time is going to be equal to, let's say, 5.1 seconds. Then the position of this object at 5.1 seconds is going to be equal to 78.03. So now the average velocity of this object from point A to point B is going to be equal to the change in distance, which is 78.03 minus 75, over the change in time, which is 5.1 minus 5. And that is going to give us 30.3 meters per second. So now let's fast forward a bit. So instead of our point B being at t is equal to 5.1, why don't we try a much closer number? So now instead, let's say we want to find the average velocity between A and B, where B is going to be t is equal to 5.001. Then the position of this object at that time is going to be s of 5.001. And that is going to be equal to 75.030003. And now let's go ahead and find the average velocity between those 2 points. So that is going to be equal to the change in position. So that'll be 75.03003 minus 75 over the change in time, which is 5.001 minus 5. And that is going to give us an average velocity of 30.003 meters per second. So again, we can make the educated guess that the velocity at t equals 5 is going to be 30 meters per second based on the calculations that we've done. Now this velocity here is what we call the instantaneous velocity. And this is what you would see on the speedometer of your car when you're driving it. So what is the big idea here? The big idea is we're trying to find what value does a ratio approach as the interval shrinks to 0. So in our first context of the geometry problem, we started with the slope of the secant line. And then what happened was that we started shrinking our interval so that it got smaller and smaller until the 2 points overlap, and that is what we call the tangent slope. Now in the second physical problem, we started with the average velocity. And what we did was we started shrinking the time interval. So we looked at shorter and shorter time until the 2 times overlap, and what we got is what we call the instantaneous velocity. And both of these problems reduces to the same question, which is what happens when the interval shrinks to 0. Now we all know that we can't divide it by 0. So this idea, which is approaching a value without actually reaching it, is the foundation of limits. And so far, we've been using phrases like as the second point gets closer and closer, or as the time approaches a single instant. But mathematically, we need a precise way to express this idea. And that language is the limit notation. We'll spend the next set of videos extensively learning about the notation of limits, how to work with them, and what they can be used for in calculus. And now let's do a quick recap of what we covered in this video. So we didn't formally define limits, and that was intentional. Instead, we focused on 2 contexts where limits will be needed. We saw how curves don't have slopes the same way that linear lines do. And while average velocity is great, it doesn't tell us the full story. Because let's say you got to your friend's house at an average speed of 60 kilometers an hour, it doesn't mean that you're driving at that speed the entire time. You could be driving slower on the smaller streets and driving faster when you're on the highway. So that instantaneous velocity is what tells us what your speed is at any particular moment in time. This next playlist will unpack all these things involving limit notation. And I hope you're ready because this is going to be a fun one. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.